Today we're going to talk about 3.2 polynomial functions and their graphs. So we are going to do, this is going to be a two-part video, okay? And I'll tell you where the other video will start at, but this is going to be a two-part video. Alright, so in this one we're going to identify polynomial functions, recognize characteristics of graphs of polynomial functions, determine end behavior, use factoring to find zeros of polynomial functions, identify zeros and their multiplicities, understand the relationship between degree and turning points, and graph polynomial functions. So the graphing part will be a separate video. Alright, so let's talk about how to identify polynomial functions. We're going to let n be a non-negative integer and let all these a's be real numbers. An cannot be equal to 0. So an is the leading coefficient here. Hold on, let me get my pen. Uh-oh. Pen. Alright, so this number here cannot be 0. And then this number here cannot be negative. If you have a negative exponent, it's written like this, 1 over x. So anytime you see 1 over x or 2 over x, anytime x is in the denominator, that means that it has a negative exponent. So if it has a negative exponent, it's not a polynomial function. Otherwise, if it's positive, then it is a polynomial function of degree n. This an is the coefficient of the variable to the highest power, and that's called the leading coefficients. So polynomial functions of degree 2 or higher have graphs that are smooth and continuous. So by smooth, we mean the graphs contain only rounded curves with no sharp corners. By continuous, we mean that the graphs have no breaks and can be drawn without lifting your pencil. So this is an example of a polynomial function. So I'm going to draw a graph. Okay? Hold on, let me make this straight. I'm going to do it one more time. Sorry. I can't really draw on this thing. Alright. So I'm going to go down, up, back up, and down. Alright, so this is a polynomial function because basically if you can take your pencil and draw it without lifting your pencil from off the paper, then it's continuous and smooth. So an example of one that would not be continuous would be something like this. You see, I had to lift my pencil off the paper in order to draw these two graphs. Okay, so this is not continuous. Okay, this one I didn't have. The first one I did not have to lift my pencil. All right, so the next thing we're going to talk about is determining end behavior. The behavior of the graph of a function to the far left or the far right is called the end behavior. Although the graph of a polynomial function may have intervals where it increases or decreases, the graph will eventually rise or fall without bound as it moves far to the left or far to the right. So basically, the leading coefficient and the exponent of your very first term, remember you have to have this in decreasing order by exponents. So the first term should have the highest exponent and then the coefficient. These two will tell you how the end behavior is. So when I mean end behavior, if you go back to this graph here, like this end behavior here and this end behavior here, how does it rise or how does it fall? Okay, so you're going to do a leading coefficient test, and as x increases or decreases without bound, the graph of the polynomial function will eventually rise or fall. So once again, you're going to look at the first term, this term here. Okay, you have two different scenarios. Well, actually you have four. So if your exponent If this exponent is odd and the leading coefficient is positive, then your graph will fall to the left and rise to the right. And this is what you see here. It falls to the left, rises to the right. If the leading coefficient is negative and the exponent is odd, it rises to the left, falls to the right. Okay? Now, if n is even and the leading number, the number in front is positive, your n behavior is where they both rise. They rise to the right, rise to the left. If n is even and the leading coefficient is negative, then the graph will fall to the left and fall to the right. So that's why you see these little arrows. So this is the table that gives you some indication of how your graph will be. So in this one, your leading coefficient is positive, n is odd. It falls to the left, rises right. So falls left, rises right. And this is indicated by the little arrows. Here, n is even, your coefficient is positive, they both rise right. All right. So in this one, your leading coefficient is negative. As you can see, it's less than 0. And as you can see, it rises right. Sorry, it rises left. Let me erase this. Rises left and falls right. In this one, your leading coefficient is negative and your n is even. They both fall. Sorry. They both fall. They both fall. So in this one, I should have put both. They both rise. Sorry. Don't put both rise right. Just put they both rise. And for the second one, they both fall. Okay, so the same behavior at each end. All right, so make sure you memorize this little table. All right, so let's look at this first problem. We have f of x is equal to x to the fourth minus 4x squared. Now, on your homeworks, it will not give you a graph of some of these problems. I just put the graph so you can see how it will rise or fall. So, in this problem, the leading term is 1x to the fourth. This is even. This is positive. So if you go back to your table, if it's even and positive, they both rise. And as you can see, they both ends rise. So rises left and rises right. Okay, so that's basically what you have to look at, the leading term. And this next one, we have x cubed plus 3x squared minus x minus 3. This number is odd, and this number is positive. So if it is odd and positive, that means it falls left, rises right. Falls left, rises right. And as you can see in this picture, that's what it does. Falls left, rises right. In this next one, we have negative x cubed minus x squared plus 5x minus 3. This is the leading term. This is odd, and this is negative. So if it's odd and negative, that means it rises left, falls right. Rises left, falls right. And as you can see, that's in the picture. This rises left and it falls on the right hand side. So rises left, I'll write it on here, rises left, falls right. And this next one, we have negative x to the fourth plus x squared. So this is even. and this is negative. So they both should fall. Falls left and falls right. And as you can see, that's what you see on this picture. Falls left, falls right. All right. So in this next problem, we're still going to do the leading coefficient test, but in this one it's in factored form. You don't have to multiply it out. Just leave it as is. This is factored form. Do not multiply out. Okay? So in this case, the leading coefficient is 4. Sorry, negative 4. The leading coefficient is negative 4. And to figure out the highest degree or the highest exponent, you're going to add the exponents that you see. Now, this on this x plus 5, there's a 1 here, you just don't see it. So you need to put that 1 there. So if we add the exponents, we get 3 plus 2 plus 1, which is 6. And that will be even. So your leading coefficient is negative and your degree is 6. Your highest exponent is 6. So this means that it falls left and falls right. So as you can see, there's no graph given. If you were to graph this, this is how it would be. Your end behavior will be pointing to the bottom. And the next one we have 2x cubed times x minus 1 times x plus 5. So the leading coefficient is 2. And the degree of this polynomial, you're going to add the exponents. 3 plus 1 plus 1. There's 1's here, you just don't see it. So you can write it in. We get 5. And this is odd. Your 2 is positive. So if your degree is odd and the leading coefficient is positive, that means it falls left and rises right. Alright, so now we're going to talk about the zeros of polynomial functions. If f is a polynomial function, then the values for x for which f of x is equal to 0 are called the zeros of f. These values of x are the roots or the solutions of the polynomial equation f of x is equal to 0. Each real root of the polynomial appears as an x-intercept of the graph of the polynomial function. Okay, so if you remember going back to finding x-intercepts, to figure out the x-intercepts, we set y equal to 0. Y is the same as f of x. So basically you're trying to figure out the x-intercepts of your polynomial function. So in this first problem, we're going to figure out all the zeros or all of the exponents, x-intercepts, for this polynomial function x cubed plus 2x squared minus 4x minus 8. So we're going to set f of x equal to 0. Which basically means x cubed plus 2x squared minus 4x minus 8 is equal to 0. In order to solve this, we're going to factor by grouping. So this is something that you're expected to know. So what I'm going to do is I'm going to group the first two. Oops. And then I'm going to group the second two. Let me write that up. Let me get the eraser out. That'll look funny. There we go. All right. So in this first group, it looks like I can factor out an x squared. I'm left with x plus 2. X plus 2. In this second group, I can factor out a negative 4. I'm left with x plus 2. As you can see, x plus 2 is common in both groups. We're going to factor that out. we're left with x squared minus 4. X squared minus 4 is a difference of squares. So this factors into x plus 2, x plus 2, x minus 2 equal to 0. So what you can do now is you can set each one of your factors equal to 0. As you can see, you have x plus 2 twice, so you only need to solve it once. So you can set x plus 2 equal to 0 and x minus 2 equal to 0. This is negative 2, this is positive 2. So when it asks you for your zeros of f, that's when you solve for the x-intercept. So in this case, x is equal to negative 2 and x is equal to 2. Let's try another one. We have f of x is equal to x to the fourth minus 4x squared. I'm going to set this function equal to 0, and I'm going to solve for x. So the first thing I can do is I can factor out an x squared. I'm left with x squared minus 4 is equal to 0. X squared minus 4 can be factored into x plus 2, x minus 2. So now we have all of our factors. I'm going to set each one equal to 0 and solve for x. Well, x squared equal to 0, if you solve this, it would just be x equal to 0. The only number you can square to get a 0 will be 0. And here x is negative 2 and here is x is 2. So you get 3 x-intercepts, or 3 zeros in this case. So in the next objective talks about how to identify zeros and their multiplicities. So in factoring the equation for the polynomial function f, if the same factor x minus r occurs x times but not x plus, okay, let me read that over. In factoring the equation for the polynomial function f, if the same factor x minus r occurs k times but not k plus 1 times, we call r a zero with multiplicity k. So now this wording might seem confusing, but once I explain it, it makes more sense. So if r is a zero of even multiplicity, then the graph touches the x-axis and turns around. Okay? If r is a zero with odd multiplicity, the graph crosses the x-axis at r. So it's two different kinds. So when I say touch the x-axis, that means something like this. I touched the x-axis and I came back around. So as you can see, this is touching the x-axis. This is the x-axis here. When I say it crosses the x-axis, I mean something like this. It actually crosses and then comes back around, or it may not come back around. But at this point, it crosses. Here, in this one, it touches. Touches, crosses. So with these zeros, we can determine whether or not it's going to touch or actually cross. So let's look at this first problem. We're going to find the zeros of f of x is equal to 1/2 x plus 1 times 2x minus 3 squared. We're going to give the multiplicities of each zeros, and then we're going to state whether or not the graph crosses the x-axis or touches the x-axis and turns around at each zero. Alright, so this is factored. You don't have to multiply it out. Since this is great that it's factored, because this gives us, it's easier to figure out what the zeros are. So I'll write it again here. I'm going to set this equal to 0. So since it's already factored, I can take x plus 1 equal to 0, and I can take 2x minus 3 equal to 0 and solve for x. Here, x is equal to negative 1. Here, I'm going to add 3 to both sides. I get x is equal to 3 over 2. So how do we determine the multiplicity? Basically, the multiplicity is how many times does this appear in your equation. So if you look at x plus 1, it only appears once. There's an exponent of 1 here, you just don't see it. So you have a multiplicity of 1. Here, 2x minus 3, it has an exponent of 2. So this is multiplicity of 2. All right, so that means 2x minus 3 appears twice in the equation. So if you solved it for x, you have 3 over 2 and another 3 over 2 because 2x minus 3 is squared. Okay, so now multiplicity of 1 is odd. If you go back to what I said earlier, if r is a 0 with of odd multiplicity, the graph crosses the x-axis at r. So that means it actually crosses the x-axis at x is equal to negative 1. So graph crosses x-axis at x is equal to negative 1. Here, this is a multiplicity of 2. 2 is even. So since it's even, if you go back to what I said earlier, if it's even, it's going to touch the x-axis. So that means this graph is going to touch the x-axis at 3 over 2 and then turn around. So graph touches the x-axis at 3 over 2. 3 over 2 is the same as 1.5. So I actually graphed this, and as you can see, it crosses the x-axis. This is the point negative 1. Your graph crosses this x-axis. This point here is 3 over 2, or 1.5. As you can see, the graph touches at 3.5, then it goes back up. Okay. In this next problem, we have negative 4 x plus 2 squared x minus 5 cubed. I'm going to set each one of these equal to 0 and solve for x. I get x is equal to negative 1/2, and I get x is equal to 5. This first one has a multiplicity of 2. This one has a multiplicity of 3. Okay, I'm looking at the exponents. Since 2 is even, that means your graph is going to touch the x-axis at negative 1/2. Here, this 3 is odd. And since it's odd, that means it's going to cross at x is equal to 5. So I already have the graph here. As you can see, the graph touches at negative 1/2. That's right here. And then it actually crosses at 5. This is the point 5. And it crosses the graph at 5. All right. So the next part talks about the turning points of polynomial functions. In general, if f is a polynomial function of degree n, then the graph of f has at most n minus 1 turning points. And we're going to keep that in mind when we do this next video. Okay? Degree n, that's your highest degree of your polynomial. So whatever the highest exponent is, you subtract it from 1. That tells you how many turning points. You subtract 1 from it, I'm sorry, and that tells you how many turning points you have. Alright, so watch out for the next video. This is the end of this video.